right, I'm going to do number 25 from classwork 3.3. So this was starting to talk about universal gravitation. Okay, so universal gravitation is just the idea that any two objects in the universe are attracted to each other by a force due to gravity that is relative to this giant gravitational constant. Well, actually, it's a very small number, but a gravitational constant. The masses of the two objects and how far apart they are from each other squared. And this is really how far apart their centers of mass are from one another. Okay, so if we have two objects that are extremely far away from each other in the universe, so even like the sun and the earth, then they're so far away from each other that we can relatively ignore the radius of each of the planets or the distance to their centers. Okay. However, if we have an object like we have in this problem, where it says we have a spacecraft that's fairly close to Earth, so here's Earth, right? And there is, like a satellite or something out here, okay? The distance between the Earth and the object, it would be important that we take into consideration the center of mass of the Earth, or the radius of the Earth, whereas the satellite is relatively so tiny that its center of mass would be negligible, okay? So in this problem, it says it's 12,800 kilometers away, or 2 Earth radii away, okay? Which means Earth's radius is 6,400 kilometers. Okay, so the total distance, or r, that we have in this problem is equivalent to 19,200 kilometers. Okay, and we need this in meters, and I'm going to kind of want to put it in scientific notation so I don't have this giant number. So let's just go ahead and do that and convert it. So we go 1, 2, 3, 4. So I've got 1.92 times 10 to the 4th kilometers. But remember, if we're going to convert from kilometers to meters, we're going to have to multiply this by 10 to the 3rd. So we just add the exponents. So the actual distance these things are away from each other is 1.92 times 10 to the 7th meters. Okay? Now, it gives us the mass of the spaceship. It says the mass of the spaceship is 1,400 kilograms. Okay? And we want to know the force due to gravity. So we're trying to find this. Okay? So we have force due to gravity is equal to G, which is 6.67 times 10 to the negative 11th, times the mass of the spaceship, times the mass of the Earth, which is 6 times 10 to the 24th kilograms. I'm pretty sure. Let me just double check. It's in the front of our textbook, so the Earth's mass, 5.97. So 6 times 10 to the 24th kilograms. And then all over this number squared. Now, I'll tell you that the majority of problems that people come across is not really, first of all, understanding and interpreting the problem correctly. Okay, that's essential. But also not plugging this into our calculator correctly. So let's go ahead and look at the calculator. I always like to break things up and just write the answer down, just so that I'm not worried about parentheses and scientific notation, all that. So the first thing I'm going to do is take this number and square it. Okay? So for that, I get 3.68 times 10 to the 14th. Okay? Now I can easily plug in all these numbers and not worrying about when my square comes before or after, or if I need parentheses or anything like that. So I just take 6.7 e to the negative 11th times 1400 times 6 e to the 24th divided by 3.68 e to the 14th, which gives me 1,523 newtons about. So the force due to gravity is about 1,523 newtons. And the next time I'll turn my phone off so it doesn't ring in the middle of the problem.